Okay, we will do 9.2, 9.3, and very likely we, for sure with parabola. And I hope you already watched the lecture video. So let's start with the material right away. 9.2, arithmetic. Sequences and series. Definition, just to remind us, a sequence is arithmetic if it has common differences. I should say common difference. Basically, the next term minus the current term equals to constant d. Okay, or we can also say that the next term is the current term plus a constant d. So pictorially, like if you try to imagine that, then the first term to the second term, you add d. The second term to the third term, you add d again. And so on and so forth. Okay, such that the sequence actually looks like the first term, the second term is the first term plus d, the third term is the first term plus twice the d, the fourth term is the first term plus 3 times the d, the first term, and then you jump 3 times. Okay, such that the nth term is basically the first term plus n minus 1 d. Okay, now let's do some examples from our textbook on the sequence part first. For example, we take number 5. Number 5, we have the sequence 16, 13, 10, 7. Now you see that we keep on subtracting by 3, right? Keep on subtracting by 3. Okay, now then the first term is 16. The common difference is -3. So the nth term is, you know what, let me do it below that. So the nth term will be the first term plus n minus 1 times the common difference. And then we simplify. Now you see that it actually mimics linear equation. I mean linear function. Right? Do you see that? Okay, so every terms that looks like linear, that mimics linear function, will be an arithmetic sequence. Okay, now they ask here, beside finding the nth term, find the fifth term, find the 10th term. Oh, which is basically just plug in numbers. Okay, by the way, this n here, it looks like there's the same, like, no, it's supposed to be subscript. So smaller and lower. Okay, so the fifth term will be -3 times 5 plus 19, that's +4. The 10th term will be -3 times 10 plus 19, that's -11. So that's for number 5. Number 13. We have natural log of 3, natural log of 9, natural log of 27, natural log of 81. But if we simplify this a little bit, this sequence is natural log of 3, natural log of 3 squared, natural log of 3 cubed, natural log of 3 to the 4th, which simplifies to be natural log of 3, 2 natural log of 3, 3 natural log of 3, 4 natural log of 3, right? And you see from there, the first term is natural log of 3. And the common difference is natural log of 3 also. Do you see that? Because every time you go to the next term, you add natural log of 3, right? Now, so the nth term will be, the general term will be the first term plus n minus 1 times the common difference. But then when we simplify this, we will get n times natural log of 3. Okay, so the fifth term will be 5 natural log of 3. The 10th term will be 10 natural log of 3. Okay, now let's see number 19. Let's see number 19. Where's my pointer? Okay, number 19. The given is that the sixth term is 2.7. I think I want to say that it is arithmetic first. Well, this section is all arithmetic, okay? So the sixth term is 2.7. And then the seventh term, that's way too easy. The seventh term is 5.2. So the question is find the first term. Okay. We know that the sixth term is the first term plus 5 times the difference. That's 2.7. While the seventh term is the first term plus 6 times the differences. That's 5.2. Now, if you subtract, okay, you see the a sub 1, the first term cancels. So you get negative d equals to negative 2.5. So the common difference is 2.5. Now then you plug that into either one of them, let's say the sixth term, right? So that's the first term plus 5 times 2.5 equals to 2.7. So the first term plus 12.5 equals to 2.7. So the first term is 2.7 minus 12.5. Okay, that's negative 9.8, I believe. Okay, so the idea is you set up the system of equations first. Okay, let's say number 23. I think this number 23, the numbers are a lot larger, so it makes us think better. Okay, the eighth term is 201. The 317th term, 2,364. And the question is find the 410th term. So let's set up the equation first. This 8th term is the first term plus 7 times the common differences. That's 210. The 317th term is the first term plus 316 common differences. So when we subtract, we get negative 309 times the common differences equals to 201 minus 2364. That's negative 2163. So the common difference will be 7. Okay, but I still need to find, I actually need to find the first term first and then get the common terms. Okay, let me do standard way. Okay, so let me put it in the 8th term. So the first term plus 49 equals to 201. So the first term is 152. So the general term is the first term plus n minus 1 times common difference 7. Boom. The nth term is 7n plus 145. Now, therefore, the 410th term is 7 times 410 plus 145. That will be 3015. Okay, I think this is the standard procedure. This is the standard procedure. Okay, now the variations, if you happen to be able to imagine that, now I want you to realize the following. You already have the 3017 term, right? Now, how many times do you need to jump to get the 410th term? Can you imagine that? You need to add 93 Ds. Is it right? Okay, 317th is the first term plus 316 Ds, right? While the 410 is the first term plus 409 Ds. Is it right? So if you subtract 317 minus 410 term, that's negative 93 Ds. But you know this already, right? You know this already. This is 2364 minus the thing that I need equals to negative 93 times 7. Do you see that? So you can use that to find the 410 term. Yeah, you can, if you picture that using this, so what I'm doing in the blue here is actually more into your conceptual view. You will see that 410th term equals to the 317 plus 93D. Okay, so you don't need to actually find the general term, even though if you offer me, that's what I will do. Yeah, that's what I will do. That's what I will do. The one you write in black is the one you tend to do when you are taking a regular test, like class tests, like in class. However, the one I wrote in blue tends to be the method you use if you take, for example, SAT or in your case, maybe GRE. So one day if you take GRE, right? GRE or other standardized tests, you know, then that's the method you use. Okay. I know that UC system already get rid of SAT. Okay, UC system already get rid of SAT, but there's no guarantee that they will get rid of GRE. GRE is the graduate record examination. So after you have your bachelor and you want to go for masters or PhDs, then they will ask you to take a standardized test. That's to overcome the great inflation and how to say it, the curriculum from different universities are different, right? But there are some standard knowledge you need to know. Now, then that's why they have that GRE, okay, to make sure that not only you have your bachelor, but you really know you have the quality of a bachelor. Okay, now the thing is GRE type of questions, pretty similar to SAT, in which one question approximately 1 minute. Okay, now if you do your things using black color, the one I do here, you may not have enough time. Okay, so that's a textbook method. That's a textbook method, the one I did in black. Okay, the one I did in blue is more into conceptual approach, which is what you really need when you take SAT, GRE later on. Okay, now next. Series. Let's define as n to be the nth partial sum. Which means the sum of the first n terms. And this S sub n is not only for arithmetic sequence, arithmetic series. No, that's actually a common notation. Okay, so the next section we will see geometric series. We will still use the same notation, and we still use exactly the same notation, even when you are in calculus 2. You know, I'm currently teaching calculus 2, right? And this is what we do in the last chapter of that calculus 2. Sequence and series, okay, infinite sequence and series, and yes, we use that partial sum idea. Now, the formula, if so, let a sub n the sequence be an arithmetic sequence, then the nth partial sum is equals to the number of terms divided by 2 times the first term plus the last term. Okay, now of course we also know that a sub n is the first term plus n minus 1 common difference, right? So we may modify this formula later on to be n over 2 times the first term plus the first term plus n minus 1d, which simplifies to be 2 times the first term plus n minus 1 times d. You can see that modification, but usually the one you really need to memorize is this one. Okay, now the proof, which is the one I like, proof. Let's say I have that summation, the sum of the first nth term. Okay, that's a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n minus 2 plus a sub n minus 1 plus a sub n, right? That's the sum of the first n terms. Now, the thing is, because a sub n, the sequence is arithmetic, then what happened is we have the first term plus the first term plus d, plus the third term is the first term plus twice the common difference, all the way until we have the second from the last term will be the first term plus n minus 3d. The first term plus n minus 2d. The first term plus n minus 1d for a sub n. Now, if I simplify those last three terms that we see here, we just want to see a pattern. Then this will be the first term plus n times d minus 3d. The first term plus nd minus twice the common difference. The first term plus nd minus d. Now, what I need you to see is the following. Notice that the sum of the first term and the last term, that is twice the first term plus nd minus d. Okay, notice that that's basically just the first term plus the last term, right? Okay, happens to be the same to the sum of the second term and the second from the last term. Okay, so the sum of the second term plus the second from the last is equal to, the second from the last should be a sub n minus 1. Okay, is equals to the first term plus the last term. And likewise, for this, you will see that this is twice the first term plus nd minus d. That's the same to the first term plus the last term. While it is actually the third term plus the third from the last. Okay. So this is basically equals to the number of pairs times the first plus the last term. Now, the number of pairs is the number of elements, the number of terms to add divided by 2. That's how we get that formula. Okay, now I know what I do here is very abstract. So while I give you the idea, it may not be that well to visualize yet. So let's do an example. Let's do an example. Let's say, for example, we have arithmetic sequence, let's say 3 and then 7. I keep on adding 4. Okay, keep on adding 4, keep on adding 4, keep on adding 4, keep on adding 4, keep on adding 4. Okay, now suppose, so this is arithmetic, right? You see that we keep on adding 4, we keep on adding 4, keep on adding 4. Okay, that's arithmetic. Now then, what is the sum? So there are 7 terms here, right? What is the sum? The sum of these first 7 terms is 7 divided by 2, because there are 1, 2, 3.5 pairs. Okay, each pair, the sum is 30. How do you get that 30? Each pair, the sum is 3 plus 27. Okay, so the sum of the first 7 terms will be 105. Now, suppose you have, let's say, 50 terms instead. Suppose you have 50 terms instead. Then what is the sum of the first 50 terms? That would be 50 terms divided by 2. The first term is 3. Now, I don't know what is the 50th term, right? What is the 50th term? I don't know, but I can use formula. That's the first term plus 49 times jumping of the difference. This is my 50th term. Okay, so that is equals to 25 times, what's that? 49 times 4 plus 6. 202. So that will be 50-50. Okay, now the thing that our textbook does not mention, I really think our textbook does not mention this. Yeah, our textbook does not mention this. But this is actually really nice to know. So let me write it in blue. Okay, so the average of arithmetic sequence is, so the average of the first n terms of arithmetic sequence, to our surprise, is equal to 1/2 the first term plus the last term. Why? Because the average of the first n partials, the first n arithmetic sequence is the sum divided by the count, right? Just that simple. So that's 1/2 the first term plus the last term. Now you can see here, for example, what is the average of these 7 terms here? What is the average of these 7 terms? Now, of course, what you do first is you take the sum, right? The average of the first 7 terms is you take the sum, which is 105, divided by 7. That's 15. Surprise. So if somebody asks you this question, okay, I have like GRE, SAT type of question in mind. Suppose somebody asks you, find the average of the first 1,000 even integers, positive even integers. Well, then the first term is 2. The 1,000th term must be 2,000, is it right? So what is the average? The average of this first 1,000 even positive even integers is 2 plus 2,000 divided by 2. That's 1001. That's it. That's it. Now, usually in GRE or SAT, they will not tell you to do the first average, the average of the first 1000 even integers. They usually don't do it that way because it's clear if they give you 1000, then there must be a formula. So usually they trick you a little bit, give you a false sense of security. They make it the average of the first, let's say 30 even integers. Now, why they use smaller number? Because then you will be tricked into listing all positive even integers, 30 of them, and then use your calculator to add them. Then you will spend so much time in punching your calculator, and then you need to check, make sure that you don't punch it incorrectly, and then divide by 30. You see? But if you think about it, we can do it really fast. The first term is 2, the last term is 60, divided by 2. That's 31. End of story. Okay, if you don't believe me, you can do that. You can actually manually add them and then divide by 30. Okay, but then even though you and I get the same answer, but I will be laughing at you because you already spent like a couple minutes, which means you sacrificed other questions to do this problem. So remember, I hope all of you listen to this, including our SI leader, because I know eventually he will go to graduate study. Okay, when you take your GRE, every standardized test, it must be time, right? You have time restriction. Okay, so if you complain about Thomas, your time is too strict, I don't have enough time, well, then go take your GRE, go take your SAT. Why don't you complain to them? Why you complain to me when I do the same thing? Okay, now that's because what? Because they want you to have that basic, for them, is basic conceptual understanding, not just textbook understanding, but conceptual understanding on how to do stuff. Okay. I need to sneeze. Give me a second. Oh. Now that also, if you think about it, that's also true for the following. If I have arithmetic sequence, right? If I have arithmetic sequence, let's say 3 and then 15, and you tell me to put a number in between. Now you can do all the arithmetic you like. What I'm teaching you here is not in our textbook. But once it is arithmetic, then this number here must have the same distance there, the same distance there, right? You subtract by D here, you add by D here, right? Okay, so this guy must be the midpoint. Does it make sense? Must be the midpoint, right? So that's plus 6. Now you see that's plus 6, right? Okay. Now suppose what I tell you, this is if you have multiple choice question that you don't need to show work, that's how you do it. Okay. So again, if you have 3 and then you have 15, they tell you to fill something in between. Okay, if what is the number in the middle? They call that arithmetic mean. Okay, such that it forms an arithmetic sequence. Then it must be the midpoint, right? That's how you get that 9. Now the thing is, sometimes what they ask you is to insert, instead of only 1, they want you to insert, let's say 3. So you figure out this way. You figure it this way. Okay, then the midpoint must be here. This is the midpoint, right? And then you compute, that's 9. Now the thing is, this must be the midpoint of these two, right? So it must be 6. You add 3, so I add 3, I add 3. So that's the 3 arithmetic means between 3 and 5, 3 and 15. Okay, now this qualify to be GRE and SAT question. Why? Because if you understand what to do, it will take you less than 1 minute to solve this problem. But if you don't know what to do, you still can solve this, but it will take you 2 or 3 minutes. And that's where you get tricked, because a lot of students, when they take GRE, they just think, oh, I know how to do that problem. They don't realize that they take too long, such that if you have 10 problems for 10 minutes, okay, and the first problem already take 3 minutes, you already take the quota, the time quota for 3 questions just to answer one of them. It means to answer that one question, you sacrifice the other 2. I hope you realize that, though. That's why students who argue, Thomas, I know how to do it, I just don't have enough time. Well, that's the way I train you. First, I train you for calculus, right? Okay, and when it comes to calculus, your teacher will not wait. They just go on explanation. The reason some students say, well, some students don't study enough, okay, then they don't gain the speed. But some students, even when they study, they gain the speed, but still not good enough, because they do it textbook way. Okay, now I know at Santa Monica and at West LA College, calculus instructors are quite reasonable for those students who only study from the book without instinct. But once you are in my calculus 3, well, I assume you have that instinct. Okay, now let's do problems from going back to our textbook. So for the last 10-15 minutes, I discussed things that's not in our textbook. Okay, let's see number 27. Number 27. The first term is -9. The 10th term is 15. Find the sum of the first 10 terms. I'm smiling. We know there are 10 terms. Divided by 2. The first term is -9. The last term is 15. 5 times 6 is 30. I don't even find what is the common difference. Yeah, I don't even need to find what's the common difference. And then number 29. The 7th term is 7/3. The common difference is -2/3, and we need to find the sum of the 15th term. Okay, let's do it. I need to find what is the first term first, right? But the 7th term is the first term plus 6 times the common difference. So 7/3 equals to the first term plus 6 times -2/3. So the first term is 19/3. How about the 15th term? How about the 15th term? You can find the general term first, okay? Which most students tend to do. But I will say, you know what? I have the 7th term, right? How many times I need to jump to get to the 15th term? 8 times, right? So the 7th term, I need to jump 8 times to get the 15th term, right? Now, the reason I do this, because I already have the 7th term, which is 7/3, and I already have the common difference. Okay, so the sum of the first 15 terms will be 15/2, the first term 19/3, the 15th term is 9/3. So that's 150/6. That's 25. Now, don't memorize what I do here. Don't memorize what I do here. The idea is I need to find the first term. That's how we get it. And the 15th term. Now, how to find the 15th term? How to find the 15 terms? You can find the common, well, you actually have that. The 15th term is the first term plus 14 times the common difference, right? Okay, so the 15th term is 19 over 3 plus 14 times negative 2/3. That's 28. Yeah, that's still negative 7 over 3. Okay. So that's the one way. This is another way to find the 15th term. Now let's go to a more interesting one. What happens if we have question like number 33? They write it in summation notation. Now here you need to be able to identify that. The sum, the first, the 18th partial sum of 1/2 k plus 7. Now here then you see, oh, you know what? The terms that I need to add, this mimics linear function. So the terms, the sequence is arithmetic. And the series is arithmetic series, right? Okay, so let's see what is the first term. The first term is 1/2 times 1 plus 7. The last term is 1/2 times 18 plus 7. Do you see that? That's 7.5 in the first term. The last term is 9 plus 7 is 16. So that must be equals to 18 terms divided by 2, the first term. Oh, just 7.5. The first term plus the last term. So that's 9 times 23.5. So the key here is to identify that, how do we identify that it is an arithmetic series? Then using arithmetic series formula, we compute that. Number 39. Oh, you know what? Now I remember another type of question. Suppose, for example, I have the summation from k equals to 7, let's say, to k equals to 41 of, let's say, 3k minus, let's say, 12, or no, maybe 11. So this is not the first 41 terms, the sum of the first 41 terms, because you don't start from 1, you start from 7. Now there are two different ways to attack this problem. The one I prefer, the one I like is this. You identify, hey, this is arithmetic. Right? Okay, now what is the first term? The first term is 3 times 7 minus 11. That's the first term. The last term is 3 times 41 minus 11. Okay, so that's 10 all the way to, I don't know what's that. 3 times 41 minus 11 is 112. Okay, so because it's arithmetic, then it will be the number of terms divided by 2 times the first term plus the last term. Now, the thing is, how many terms there if you don't start from 1? Well, the number of terms will be 41 minus 7. Don't forget plus 1. 41 minus 7 tells us the number of terms after the first term. Okay, like just take a look here. How many terms here? From 1 to 18. If you subtract 18 minus 1, you will get only 17, but you know there are 18 terms there. Okay, that's why after you subtract, you still add 1. Okay, so this is equal to, what's that? 41 minus 7 plus 1, that's 35 times 122 divided by 2. That's 2,135. Okay, that's how I prefer to do it. So basically you write them down first. You write this out first. Okay, to see what is the first term, what is the last term, and the only thing still missing is how many terms you have in between. Okay, but the number of terms is this number on the top minus the number at the bottom, and then you add 1. Okay, and then the next part is let's see number 39. Number 39. We have 4 plus 11 plus 18 all the way to 466. Express this in using summation notation, using the sigma notation. So then let's say identify it first if we can see the pattern. So you add 7 here, you add 7 here. So you keep on adding 7. Okay, so the first term is 4. The common difference is 7. Now, the thing is, you need to know how many terms here. So this is term number what? Right? You want to know that's term number what? Okay, so then the nth term, the last term is the first term plus n minus 1 times d. Is that right? Now that is equals to 466. Okay, when I simplify the left-hand side, 7n minus 3 equals to 466. 7n is 469. So n is equals to 67. There are 67 terms there. So the summation notation now becomes the sum from n equals to 1 to infinity. The first term is 4 times n minus 1, common difference 7, which of course we simplify, right? I'm sorry, not infinity, 67. Or you can find the nth term first. This is 7n minus 3. Okay, that's for number 39. Now, number 41, however, it is not arithmetic. 3 over 7 plus 6 over 11 plus 9 over 15 and on. It is not arithmetic series. Oh, hold on, up to 18. Up to 18 over 27. However, the numerator follows. The numerator follows arithmetic sequence. The denominator also. Okay, the numerator, you keep on adding 3. The denominator, let me call the common difference here is E. I don't like the notation. I call that D2 again. So the denominator, you keep on adding 4. Okay, so on the numerator, the A sub n is, if you do it fast, that will be 3n. You figure out, okay? But the denominator has the pattern 4n plus 3. Okay, so the summation notation here will be the summation of 3n over 4n plus 3 from n equals to 1 to n equals to, then you try to match it. What is n to make it the numerator becomes 18? 6. Right? That's the summation notation. Okay, I guess that's the, I guess that's the parts that I would like you to work on. Suggested homework from this 9.2 will be, I think number 1 to number 49 is reasonable. Number 1 to number 49. Okay, now let me take a break. I will come back at 9:10. With 9.3. 9.3, we have geometric sequence and series. 9.3, geometric sequence and series. Definition. A sequence is geometric if it has common ratio. That is, the ratio of the next term to the current term is common R. Or another way to say it, that the next term is the current term times R. And if we see the pattern, okay, idea, the first term, the second term, the third term, and on to the nth term, you see that the second term, you multiply the first term by R. Okay, So the second term is actually the first term times 1r. Now, from that second term, you multiply r again to get a third term. So the third term is actually the first term times r squared. You see, from the first term, you jump twice. But instead of adding by d, now you're multiplying by r. Okay, and so on and so forth, such that you will see that the nth term is basically, the nth term is the first term times r to the n minus 1. Okay. For example, let's see number 5. That seems to be hard. Number 5, we have the sequence 300 and then negative 30 and then 3 and then negative 0.3. So you see that we keep on dividing by negative 10, right? Okay, so the first term is 300. The common ratio is negative 1 over 10, which is negative 0.1. Okay, so the nth term is 300 times negative 0.1 to the power of n minus 1. But actually, we're supposed to clean this up though. We're supposed to clean this up. Okay, our textbook gives us this answer. Okay, but I hope you are able to clean this up a little bit, like simplify that a little bit by doing the following steps. This is 300 times negative 0.1 to the n times negative 0.1 to the negative 1, which is 300 over negative 0.1. You see that? So that's negative 3,000, negative 3,000. Okay, and then negative 0.1 to the n. Now, if you go to calculus 2 later on, then I would require you to simplify this even further. Okay, if you are in calculus 2, then I will require you to simplify this even further to be the following. You need to show the alternating sequence part. Okay, this is the alternator. Okay, number 13. We have 2 and then 2 to the x plus 1, 2 to the 2x plus 1, 2 to the 3x plus 1. That sequence is the same to 2, then 2 times 2 to the x, then 2 times 2 to the x squared, then 2 times 2 to the x cubed. Is it right? Okay, so the first term is 2. The common ratio is 2 to the x. So the nth term will be the first term times the common ratio to the n minus 1. That's 2 times 2 to the nx minus x. Which of course we can put together. We insert that 2 again. Maybe instead of writing it that way, hold on. Let me not distributing it. But this can be written as 2 to the n minus 1x plus 1. Okay, now what happens if we get two terms and we need to find the common ratio? Number 17. The fourth term is 3. The sixth term is 9, and it is geometry. We want to find, the question is find the R. But I will go ahead also find the first term. Now you see that the fourth term, which is 3, is the same to the first term times R cubed, while the sixth term, which is 9, is the first term times R to the fifth. Right? Now, you divide it. Okay, so basically when you divide, it becomes this. It becomes 3 over 9 equals to the first term times R cubed over the first term times R to the fifth. Okay, 1/3 equals to 1 over R squared. So R squared equals to 3, R equals to plus or minus square root of 3. There are two possibilities. Now, so let's call R1 equals to radical 3, R2 equals to negative radical 3. Okay, for R1 equals to radical 3, what is the first term? The fourth term, which is 3, equals to the first term times radical 3 cubed. This is 3 equals to the first term times 3 radical 3. So the first term is 1 over radical 3 or radical 3 over 3. So, so one of the first term is radical 3 over 3 with common ratio radical 3 will give us the fourth term equals to 3 and the sixth term equals to 9. Okay, but that's not the only way to make it. Another way for R2 equals to negative radical 3. So the fourth term, which is 3, equals to the first term times negative radical 3 cubed. Gada-bum, gada-boom. The first term is negative 1 over radical 3, which is negative radical 3 over 3. Okay, in other words, if your first term is negative radical 3 over 3 and the common ratio is negative radical 3, it also gives the fourth term equals to 3 and the sixth term equals to 9. Now, what if we do number 23? Let me do it here. Number 23. Suppose the fourth term is 4, the seventh term is 12. Find the 10th term. I do it long way first. Okay, the fourth term, the long way in a sense that I want to find the general term. After I get the general term, then I find the 10th term. Okay, the 7th term is the first term times r to the 6th, while the 4th term is the first term times r cubed, right? That's 12 for the 7th term. That's 4 for the 4th term, which if I divide, I will get r cubed equals to 3. So r equals to cube root of 3. Now, so what is the 10th term? Okay, let's find the first term first. The 4th term is the first term times r cubed. But we know the 4th term is 4, right? So the first term is times 3 equals to 4. The first term is 4/3. So the 10th term will be the first term times the ratio to the power of 9. That's 3 cubed, 3 squared, that's 9. So that's 36. Alternatively, this fun. This one is fun. Okay, so notice that we find the r cubed equals to 3, right? Now the thing is from the 7th term to the 10th term, you jump 3 times. Is that right? Do you notice that? From the 7th term to the 10th term, you jump 3 times. So multiply by r cubed. Okay. Now, how about the series? Now, I believe I already proved the formula for geometric series. Okay. Let the sequence be geometric. Or it is a geometric sequence. Then the nth partial sum is equals to the first term times 1 minus r to the n over 1 minus r. Now, I believe I already showed the proof in my lecture video. But just like before, I want to prove that again. I need you to really feel this proof, the elegance of this proof. Okay, now so S and the sum of the n partial sum is first term plus the second term plus the third term all the way to the nth term, which is equals to the first term plus the first term times r, the first term times r squared, all the way to the first term times r to the n minus 1. Okay, now that's the n partial sum, right? Now, suppose I multiply nth partial sum by r, this becomes a sub 1 times r, right? You multiply by r here, multiply by r here, multiply by r here. And this will be a sub 1 r to the n. Okay, now let me rewrite this. Rewrite But I try to rewrite it in a sneaky way, in a smart way. What's that? The n partial sum of geometric series, the geometric sequence is first term times r, first term times r squared, all the way to first term times r to the n minus 1. While if I multiply by r, that will be the first term times r. Notice where I write it under. So the whole sequence actually shift one place to the right. When I subtract this, I get s sub n minus r times s sub n. And we have pairs that cancels here. So the first term minus the first term r to the n. Now, don't underestimate this technique, because even in Calculus 2, you will see this technique again. It is called telescoping. It is called telescoping. Well, maybe not exactly telescoping, but that's the idea, in which like some terms in the middle cancels. Now, then I factor the n partial sum, and on the right-hand side, I factor the first term. So the nth partial sum equals to first term times 1 minus r to the n over 1 minus r. That's the proof. Okay, in fact, we can go further. If the magnitude of r is less than 1, then r to the n will go to 0 as n goes to infinity. I wonder if you remember that. That's basically because of this. If the magnitude of r is less than 1, okay, then r to the x, the function r to the x will look like this, right? Okay, now when x goes to infinity, then the y value will be 0. Okay, now, so if absolute of r is less than 1, then the infinite sum, usually denoted by s only, but you can also emphasize that's s infinity, that's equals to the first term over 1 minus r. Well, because this part here becomes 0. Now, let's do problem. Number 29. Number 29, the fourth term is 27. Common ratio is 1/3. The n is 7. The fourth term is 27. So basically find S7, the seventh partial sum. Okay, let's find the first term first. So the fourth term equals to the first term times r cubed. The fourth term is 27. The first term is what we are looking for. R cubed is 1/3 cubed. So 27 equals to the first term times 1 over 27. So the first term is 27 squared. You can easily compute that with calculator. Okay, but what is the seventh partial sum? Now the first term is 27 squared. 1 minus 1/3 to the power of 7 over 1 minus 1/3. Okay, I plug in formula. Now then, from there I compute. This is 27 squared. This is 1 minus 1 over 3 to the 7th over 2/3. Let me multiply, you know what? 27 squared is 3 cubed, 3 to the 6. If I multiply the top and the bottom by 3, then I will get 3 to the 7th, 1 minus 1/3, 1, 3 to the 7th over 2. That is 3 to the 7 minus 1 over 2. Okay, we can use calculator for that. That's 1093. Simplify that first, because if you don't simplify this, and you use your calculator, you tend to get a nasty decimal here. Okay, now that nasty decimal, if you multiply with rounded error, with some error, if you multiply by a big number, then the error gets larger. Okay, so simplify first. Simplify first. Okay, don't attack your calculator right away. You are preparing yourself for calculus, right? Okay, so you better have that pre-calculus quality for you to get there. In other words, you should not be afraid to see fractions anymore, no more. Okay, number 33. Number 33, we have the series, the sum from k equals to 0, it's not from 1 to 9 of negative 1/2 to the k plus 1. Notice that it mimics exponential function. Mimics exponential function. Right? Okay, so the series must be geometric series. Now then, to find the geometric series, let's see, what is the first term? The first term is when k equals to 0, so that's negative 1/2. And then the next term you multiply by the ratio negative 1/2, right? So it becomes positive 1/4 and on. You have 9 terms there. Okay, so using formulas, that's negative 1/2 the first term, 1 minus negative 1/2 to the 10th. There are 10 terms there. Not 9 terms, 10 terms, over 1 minus negative 1/2. Okay, so negative 1/2, 1 minus 1 over 2 to the 10th over 3/2. Let me multiply by 2 on the top and the bottom first. So I get negative 1/3, 1 minus 1 over 2 to the 10th. Let me simplify that a bit more. I will factor 1 over 2 to the 10th out. So negative 1/3, 1 over 2 to the 10th That's 2 to the 10th minus 1. Now 2 to the 10th minus 1 is 1023. If I divide that by 3, I will get 341. Negative 341 over 2 to the 10th, which is negative 341 over 1024. Don't make it decimal. Don't make it decimal. If you make it decimal, there's a chance that you do some rounding. Next one, let's see number 43, the infinite series, infinite geometry series. That's 1.5 plus 0.015 plus 0.00015 and on. You see that you multiply by 100, I'm sorry, 0.01, right? You move the decimal point twice to the left, multiply by 0.01, right? So the first term is 1.5. The common ratio is 0.01. So what is the sum? Infinite sum. The first term over 1 minus r. Okay, notice that we can use that formula because the absolute of r is less than 1. Okay, so that's 1.5 over 0.99. Move the decimal point twice. Reduce by 3. Okay, now if the magnitude of r is greater or equals to 1, then the infinite sum does not exist. Okay, then it's very likely it does not exist, but if the r is positive, then it is either positive infinity, the infinite sum is positive infinity, or negative infinity. If the r is positive, then it depends on the initial the first term. Okay, let's say for example the one I can see here is let's compare number 45. Number 45. Okay, radical 2 minus 2 plus 2 radical 8 minus 4 and on. So the first term, as you can see, is radical 2. The common ratio is negative radical 2, whose absolute value is radical 2, which is greater than 1. Okay, so what happened is we can't use that formula. No, we cannot use that anymore. In fact, you see that you keep on adding something greater than the previous value. And the sign is alternating, plus, minus, plus, minus, plus, minus. Okay, so the infinite sum later on does not exist. Because as this grow very, very big, then sometimes it is plus big number. And the next term is even bigger, negative bigger number. And after that, you add bigger number. And after that, you subtract the bigger number, right? So it's actually, you add a big number, but then you subtract by bigger number, and then you add by bigger number, and then you subtract by bigger number. Okay, we call that in calculus, we call that divergent. It doesn't go to a specific number. Okay, number 46 on the other hand, you have 1 plus 3/2 plus 9/4 and on, right? See, the first term is 1. The common ratio is 3/2, which is greater than 1. Okay, so we cannot use that formula. Okay, but we know that this, you keep on adding positive number that is larger, keep on adding positive number that is larger. So the infinite sum we know will be infinity, positive infinity. Number 49. X over 3, x squared over 9, x cubed over 27, infinite sum, where absolute of x is less than 3, which implies absolute of x over 3 is less than 1. Right? Okay, well, the ratio here is x over 3. The first term is x over 3. The common ratio is also x over 3. So the infinite sum, because the ratio is less than 1, right? Then we can do infinite sum, the first term over 1 minus the common ratio. Multiply the top and the bottom by 3, we will get x over 3 minus x. Now, let's do the fun part, the last part, and then I was actually planning to do the parabola. Should I do that later? Yeah, maybe I do the introduction to parabola. Okay, now I don't have lecture on parabola, as I remember. So there's no lecture video for you to watch for parabola. So I need to build that from ground up later on. We learned the parabola even in test before test 1, right? But now we look into a further detail about the parabola we learned before. Okay, but let's do number 53 first. Number 53, and this is, for me, this is important. The following. Sometime in the past, in our arithmetic or in pre-algebra, we learned that rational number is a number that can be expressed as an integer over a non-zero integer. And b is not 0. Okay, and one of them is this: a rational number is everything that you can rewrite as integer over non-zero integer, and one of them are terminating decimal. Terminating decimal is easy. So let's say if I have 1.47, what is that? Well, you call that a rational number, right? So it means you can rewrite that as a fraction, right? Okay, of integer over integer. Now, the problem is what happened if we have, like number 53, non-terminating but repeating decimal. Can we rewrite this into a rational number? Now, in pre-algebra, we took it by faith that it's a rational number. Okay, so even in science, though, people say, well, if you believe in science, then you don't have faith. Well, too bad. When when I taught you math, when your pre-algebra teacher talk about rational number, they just say that you have to believe it, right? And then the revelation that why it is rational number is being revealed in intermediate algebra. You're supposed to have seen this in intermediate algebra, but I present that to you again because there's a chance your instructor didn't go that far. Okay, so I will show you why this is a rational number, even though we have non-terminating but repeating decimal. Okay, but talking about faith, saying that in science we don't need faith is actually not true. Okay, at least that you accept that without proof in pre-algebra, and now we prove that. Okay, and now we prove that. In other words, simply because we cannot prove that doesn't mean it's not true. That's what I'm trying to say. Okay, simply because we cannot prove that, it doesn't mean it's true. It simply means we don't have proof. Okay, simply means we don't have proof. Now I will show you two different ways to find the rational number associated to this non-terminating but repeating decimal. The first method is a textbook method. Okay, I will show you the textbook method first. 2.417 bar is 2.417, 17, 17, 17 repeating, right? And that is equal to 2.4 plus 0.017. So this is my 2.4. This is my 2.4. This is my 17. And my next one is 17. Right? Do you see that? And so on and so forth. Now, the thing is, if you take a look here, this is actually geometric series with the first term equals to 0.017 and the common ratio 0.01. See, you multiply by 0.01. Now, in other words, then this is 2.4 plus, you see the ratio is, the magnitude of the ratio is less than 1. So we can use that infinite series formula, the first term over 1 minus the common ratio. Okay, so this is 2.4 plus 0.017 over 0.99. Let's move the decimal point 3 times to the right, or for the fractional part. So that's 17 over 990. But this is already a fraction plus a fraction, right? We know you can just compute this, which I will do. We will just compute this, but we know at the end it will be an integer over an integer, right? And therefore we have proven that it is indeed a rational number. If you have repeating decimals, non-terminating and repeating decimals, then it must be a rational number. Okay, so this is 24 times 99 plus 17 over 990. Let's see what's that. That's 2393 over 990. But you already have integer over integer, is it right? Now that's the first method. That's the first method. Now, let me show you the second method, which in my opinion, is more elegant. This is not from textbook though. Now, even though the work is not from textbook, but the proof, the work is actually coming from the way we prove geometric series. And here it is. Here it is. Let's call this x equals to 2.4171717 and on. Notice that it repeats every two numbers, right? So if I multiply both sides by 100, the decimal point will move twice to the right. Now let me rewrite it. Let me rewrite it. 100x is 241.71717 and on. While x, I will line up the decimal point. Notice that this part here cancels. You see that? Okay, so when I subtract, that part will cancel. I have 99x equals to 239.3 only. The repeating parts, they cancel. So x is equals to 239.3 over 99. But the numerator is not an integer, so let me move the decimal point once to the right on the top and at the bottom. Basically, I multiply the top and the bottom by 10. Boom. You see? Same. Okay, so suppose somebody give you this question, suppose I give you this question. Okay, let's say I have 1, 2, 3.4, 5, 6, 7 bar. What is this in in fraction? Okay, so what I will do is I will call that x first. Let x equals to that number 123.4567 bar on 567. This is equals to 123.4567567 and on. Because three number repeats, I multiply by 1000 both sides. Okay, so it becomes 123.456 point. The point moved there now. 7567567 and on. Now line up the decimal point. 1000x equals to 123.456.757 567 and on. And x itself is 123.4567567 and on. And you see that this part cancels when you subtract. So I get 999x equals to 123.333.3. So x equals to 123,333.3 over 999. Move the decimal point once to the right, multiply by 10 both sides, and actually I can divide by 3. That's 41111 over 3,330. Okay. I think that's where I will stop for 9.3 suggested homework. Number 1 to number 59. Just do every other odd, I think. But you see, it's more about formulas and how to use them. Okay. Now let me go on for the next maybe 10-15 minutes. Let me do the intro to parabola. 10.1. Intro to parabola. Give me a second. Give me a second. I will stop the recording.